Hey, everyone, and welcome back to the channel. Today, we're diving deep into one of the most fascinating and fundamental systems in our body, the autonomic nervous system. Ever wondered what makes your heart race when you're nervous? Or why your mouth gets dry? Or how your body just knows to digest your food without you even thinking about it? Well, that's the ANS at work, and we're going to unpack it all. So, what exactly is the autonomic nervous system? Think of it as your body's automatic pilot. It's the part of your peripheral nervous system that controls all the involuntary stuff, the things you do unconsciously direct. This includes your heart rate, digestion, breathing rate, salivation, and even the size of your pupils. It's working 24/7, keeping your internal environment stable, a state we call homeostasis. Without it, we'd literally have to think about every single heartbeat. Imagine that. The ANS is broadly divided into two main branches, and they read like two sides of a coin, the sympathetic nervous system and the parasympathetic nervous system. You've probably heard of the sympathetic system as the fight-or-flight response. When you perceive danger or stress, like narrowly avoiding a car accident or having to give a big presentation, this system kicks into high gear. It prepares your body for action. Your heart rate and blood pressure shoot up. Your airways open to get more oxygen. Your pupils dilate to see more clearly. And it diverts blood flow away from non-essential functions like digestion and towards your big muscles. It's all about mobilizing your body's resources for immediate, intense activity. On the flip side, we have the parasympathetic nervous system, often called the rest and digest or feed and breathe system. This one is all about conservation and housekeeping. When you're relaxed, maybe after a good meal, the parasympathetic system takes over. It slows down your heart rate, stimulates digestion, constricts your pupils, and generally promotes a state of calm. It's what helps your body recover, save energy, and carry out all the routine maintenance tasks. So, while the sympathetic system spends energy, the parasympathetic system saves it. These two systems work in a delicate balance, constantly making adjustments to meet the body's needs. Now, let's get into the nitty-gritty of how this communication happens. It all comes down to chemical messengers called neurotransmitters. The main players in the ANS are acetylcholine and norepinephrine. Think of these as the primary languages spoken by your nerve cells. The first neuron that leaves the central nervous system, called the preganglionic neuron, always uses acetylcholine in both the sympathetic and parasympathetic divisions. It's the second neuron, the postganglionic neuron, where things get different. In the parasympathetic system, this second neuron also releases acetylcholine. Simple, right? But in the sympathetic system, the postganglionic neuron primarily releases difference in neurotransmitters is key to how these two systems produce opposite effects. So, where do these chemical messages go? They bind to specific proteins on the surface of target cells called receptors. It's like a key fitting into a lock. A neurotransmitter, the key will only affect a cell if that cell has the right receptor, the lock. The two main types of receptors for acetylcholine are called cholinergic receptors. These are further divided into nicotinic and muscarinic receptors. Nicotinic receptors are found where the first and second neurons meet in both systems. Muscarinic receptors are typically what acetylcholine binds to at the final target organ in the parasympathetic system, like the heart or the gut. For norepinephrine, the receptors are called adrenergic receptors. These are the locks for the sympathetic system's key. Adrenergic receptors are split into two main families, alpha and beta receptors, which are further subdivided into alpha 1, alpha 2, beta 1, beta 2, beta 3. And this is where it gets really cool from a pharmacology perspective. Different organs have different types of adrenergic receptors. For example, your heart muscle is loaded with beta 1 receptors. When norepinephrine binds to them, it makes your heart beat faster and more forcefully. Your lungs, on the other hand, have lots of beta receptors. When stimulated, they cause your airways to relax and open up. Your blood vessels have alpha 1 receptors, which cause them to constrict and raise your blood pressure. Understanding these specific receptors is the foundation of modern pharmacology. Many of the drugs we use today are designed to either mimic or block the actions of these neurotransmitters at their receptors. Let's take a look. Drugs that mimic the effects of the sympathetic system are called sympathetic. Classic example is albuterol, the stuff in asthma inhalers. It's a beta-2 agonist, meaning it specifically activates beta-2 receptors in the lungs, causing the airways to dilate and making it easier to breathe without jacking up your heart rate too much. Another example is phenylephrine, a common decongestant. It's an alpha-1 agonist that constricts blood vessels in your nose, reducing swelling. On the other hand, drugs that block the sympathetic system are called sympathomimetics. The most famous of these are beta blockers, like propranolol or metoprolol. These drugs block beta receptors, particularly beta-1 receptors in the heart. This is why doctors prescribe them to lower blood pressure and control heart rate in patients with hypertension or certain heart conditions. They essentially put a damper on the fight-or-flight signals reaching the heart. Now, let's flip to the parasympathetic side. Drugs that mimic acetylcholine are called parasympathomimetics, or cholinergic agonists. Pilocarpine is a good example. It's used in eye drops to treat glaucoma by constricting the pupil and improving fluid drainage from the eye. Let me know in the comments if you have any questions or what topic you'd like to see next.